Chapter 5 Atmospheric Structure and Radiation Transfer, Section 5.5 Surface Albedo and Insulation. Now, we just talked about radiation passing through the atmosphere, and if the Earth's surface was black and colored, then all of that radiation would be absorbed, creating heat energy at the Earth's surface. The fact is that the Earth's surface varies in tone, and sometimes it's highly reflective. So the insulation that is being received at the Earth's surface can be of two types. It can be direct solar radiation. Direct solar radiation is solar radiation that hasn't been influenced by any of the atmospheric properties discussed in the previous section: scattering, reflection, or absorption. Or the solar radiation can reach the Earth's surface as diffuse solar radiation. So this is solar radiation that was altered by one atmospheric process, and that is scattering. You can tell that diffused solar radiation exists because if there was only direct solar radiation, your shadow that's cast from sunlight would be perfectly black in color. It isn't. It's a gray tone, indicating that radiation is not coming in directly through the atmosphere, but it has been altered by scattering and is coming in at a number of different directions that are quite different from direct sunlight. So not all of the direct and diffuse radiation available at the Earth's surface is used to do work. So some of the things that this radiation could be used to do is it could be used in photosynthesis. It could create sensible heat by absorption, so the surface of the Earth heats up, and then by conduction and convection, that heat energy is transferred up into the atmosphere and down into deeper soil and sediment. Or water could be used to evaporate water and change water from liquid to gas. Or it could be used to melt frozen water, snow and ice. But as I said, some of the radiation received by the Earth's surface is actually not received. It's redirected back to space by surface reflection. The reflectivity, or sometimes a word that's used to describe this process, albedo, of the Earth's surface varies with the type of surface, the material that covers it. For example, fresh snow is highly reflective. Up to 95% of the radiation that reaches it is sent back to space. Some other surface type albedos are dry sand, 35 to 45%. So of all the surface types that are out there, besides snow and ice, it is probably the most highly reflective. Broadleaf deciduous forest has very little reflectivity to it. It absorbs most of the radiation that it receives, or takes that radiation and uses it in photosynthesis. Needle-leaf coniferous forests are a little bit more reflective than broadleaf forests. And then grass type vegetation has a reflectivity of about 15 to 25%. If we took the entire Earth and calculate out the entire Earth's average albedo, and we're including both the surface and the atmosphere, that value would be about 30%. So here we can see the snow on the ground surface and in the trees here, and how white it is determines how reflective it is and how much radiation is being sent back to space. Our satellites that we have in space can be used to measure this albedo effect, the Earth's albedo. And I'm going to show you some slides that show albedo measured from space. And we're going to look at two different dates, January and July. So let's begin by looking at the Earth's surface, so no atmospheric effect. So in January, we can see in the high latitudes, the reflectivity is high. So colors orange to red indicate high reflectivity, and this is being caused by snow and ice that's on the ground surface. If you take a look at South America, it's in the tropics and subtropics, and in lower latitudes it's summer, very low reflectivity. On Africa, we can see two areas of high reflectivity, the Sahara desert. We can also see the Middle East is highly reflective, so a lot of sand. And then down at the southern tip of Africa, we can see a small little area of reflectivity. That's the Kalahari Desert. If you go to Australia, once again, Central Australia, highly reflective. And of course, Antarctica has the highest reflectivity in the southern hemisphere, and that's because it's covered with permanent snow and ice. Now, the reason why we don't have any measurements above roughly 65 degrees of latitude north to 90 degrees north is because it's in total darkness in January. The July image shows the summer conditions in the northern hemisphere, so that highly reflective snow and ice is gone now. There's still a bit in the Himalayas, in the Middle East, and in the Sahara Desert in terms of the northern hemisphere. And in the southern hemisphere, we because of the total darkness, and we really can't see how reflective the Antarctica is. In the July image, we can see that the sea ice that exists in the Arctic Sea is highly reflective, and the most reflective body in the northern hemisphere is Greenland, which has permanent ice and snow. These two images now include the reflectivity of the atmosphere. So it's not just the surface, we get the surface and the atmosphere in this image. And in the January image, once again, we can see that there's a lot of reflectivity being caused by snow and ice. But there's more, and that's being caused by a frequent occurrence of clouds that are generated from mid-latitude cyclones. So in that zone, centered at about 60 degrees north, we see a zone of reflectivity, and a lot of that is being generated by mid-latitude cyclones. The oceans are actually very cloud-free, so the subtropical oceans in the northern hemisphere appear to have low reflectivity. Once again, we can see the effects of the Sahara Desert, the sand, down through the center at about the equator. We can see a slight band of higher reflectivity that's being caused by thunderstorm clouds that are generated almost on a daily basis at the intertropical convergence zone. In the southern hemisphere, the Antarctica appears highly reflective, and that zone in the ocean that borders Antarctica, that once again is a zone dominated by these mid-latitude cyclones that produce a lot of cloud cover that reflects solar radiation back to space. So that's the January image. In the July image, we see the mid-latitude cyclones more or less disappear over the continents in the northern hemisphere. They become less reflective. It's still highly reflective over the oceans, or over the Arctic Sea, and over Antarctica, or sorry, not Antarctica, Greenland. In the northern Pacific and northern Atlantic, that sort of bands of reflectivity that you see over the oceans, those are mid-latitude cyclones. In the summer, they still do occur over the ocean bodies, but they don't as frequently move inland as they do in January. Once again, we can see a band of reflectivity along the intertropical convergence zone caused by the meeting of what's known as the trade winds, and this produces almost daily thunderstorms, and thunderstorms are highly reflective. We don't have complete information for the southern hemisphere in July because the satellite can't view in total darkness reflectivity. Reflectivity can't occur with darkness, but we can see there is this band just above 60 degrees south, and that once again are these mid-latitude cyclones that produce quite a bit of cloud cover.